The second part of series solutions of differential equations, and power series and analytic functions is what this lesson was about. We're going to address an analytic function. So not all functions are expressible as power series. So let's write that down. Not all functions are expressible or can be expressed as a power series. So there are certain functions that can be, and we call these analytic functions. And instead of writing that, let's just read this. So a function f is said to be analytic at x naught if it is an open interval about x naught. This function is the sum of a power series, the sum from n equals 0 to infinity of a sub n, multiplied by x minus x naught to the n, that has a positive radius of convergence. So basically, what are we talking about? A function is said to be analytic on an interval if it has a convergent power series on that interval. So we'll go ahead and get that written down. So a function is defined to be analytic if it has a convergent power series. And that's just what we've written right above. On that interval. Now, basically, we're just looking for where we fail this when we divide by 0. So let's take a look at these functions here below expressed as power series. So, of course, we know that a polynomial is analytic at every x naught. We have rational functions, p of x over q of x. So we have p of x over q of x. And these are analytic functions. Of course, except for those rational functions when q of x is equal to 0. We know, of course, all of our polynomials are analytic functions. And we can actually write those because these can be written as a naught plus a sub 1, x minus x naught, plus dot 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 a sub n, x minus x naught to the nth power. Okay, so we've got our polynomial functions, and now let's take a look at some familiar functions. These are more of our elementary functions. We have e to the x, sine of x, and cosine of x. You can see here, these are all analytic for all x. And now the natural log is analytic for x greater than 0. So you can see here, okay, so now thinking about this example, I did want to mention that if f and g are analytic, at x naught, then of course f plus g, a constant times f times g, and f divided by g, of course, with g of x not equal to 0 are also analytic. So let's go ahead. That really helps us with this example because we can now look at part A here. So in part A, we are trying to decide here if the following statements are always true or sometimes false. So basically in part A, we have a linear combination of analytic functions. So of course, this is going to be an always true. And these are the reasons, justification for our answers, and we'll put our answers up there. In part B, we have f divided by g of x, and of course, this function, f divided by g, will be analytic, but only hold true if the denominator, g of x, is not equal to 0. So, f of x over g of x will also, or will be, analytic only if g of x is not equal to 0. So we're going to put sometimes this is a false statement. Let's go ahead and look at C. F prime of x is analytic at x naught. So the derivative of an analytic function is also analytic. And this really results from the fact that the analytic function has every order of derivative at the point x naught. So they will. This will always be true. And looking at part D, we do have a combination of analytic functions. And also, so here we have a combination of analytic functions along with term-wise integration of an analytic function is also analytic. So this is always true. And that concludes this discussion of analytic functions.